All right, so here's the Newton's law of gravity. Every object in the universe attracts every other object. The magnitude of the force was given by Newton, and the magnitude of the force is the gravitational constant times the product of the masses divided by the distance between the two objects squared. So, for instance, if you double the distance between the two objects, the force, if you double the distance, it would be 2r squared. So the force would fall by a factor of 4. Okay. Now the gravitational force is very weak because this gravitational constant is very small. So if you want to see, so the gravitational constant is 6.67 times 10 to the minus 11 Newton meter square per kg squared. Okay. So if you want to see a sizable force, at least one or both the masses have to be large. Okay, so, and like I said, gravity is the weakest of the 4 forces because the gravitational force is, the gravitational constant is small. And as we mentioned, the force between this guy and his dog is of 10 to the minus 7 newtons. The force between him and Earth is 1,000 newtons, 10 billion times greater. And so, as we were saying, if you want a large force, if you want the force to be large, at least one of the masses has to be large, and the force between the Earth and the man is large. Okay. We saw this slide where Milky Way is the galaxy we live in, and our sun is somewhere over there. The galaxy is a spiral galaxy, and we are headed toward on a collision course with Andromeda, which is another spiral galaxy, and this collision will happen another 4 billion years. Okay. Now, you saw that the gravitational force between two objects is given by G m1 m2 divided by r squared. Okay. G is the gravitational constant, and it's a very small number. And actually, this constant in physics, this constant is the least accurately measured constant. Okay. And in fact, Newton gave us this law in 1687, and the gravitational constant G was not measured for 100 years, almost 110 years later. Okay, so it was that hard to measure the gravitational constant. Okay, Mr. Cavendish measured the gravitational constant, and this was his setup. Okay, and so I'll briefly mention this. I'll briefly describe the setup, how he measured G. Okay. So here was the idea. Okay, so these are two heavy spheres, and here are two light spheres at the end of a rod. Okay. Now these heavy spheres initially were low down there. Okay, so they were far away from these light spheres. Okay, so here are the two light spheres. There's the initial configuration, and these guys can be raised and lowered. So they were low and they were far away. And when they were, and then, so this was the initial position of the little spheres. And what Mr. Cavendish did was, here was the initial position, and then he raises these large spheres. And when he raises these large spheres attract these little spheres, and they move toward the large sphere. They get attracted toward the large sphere, and this thread is twisted. Okay, so this will stop once the torque exerted by these guys is equal and opposite to the torque because of the wire being twisted. Okay. And when this wire twists through a certain angle, theta, Mr. Cavendish had measured the force in the wire that come into play, the torques that come into play in the wire relating to the angle theta. Okay, you can do that. You can treat this as a torsional pendulum and find the torsion constant. Okay, so from that he could calculate the force that was being exerted. Once he could calculate the force that was being exerted, so he could calculate the force. Okay, he can measure this distance between them. He knows measure the distance between them. He can calculate the forces. He knows the masses of the spheres, and now he can calculate G. So that's how G was found. Okay. And again, like I said, this was quite hard to do. It was not done till 120 years later, after Mr. Newton gave us this law of gravity. Okay, so that's how hard it was to measure. Okay, now here's an interesting thing. So here's the Earth. Here's an object. You guys have all measured the acceleration due to gravity, which is G. Okay, so the gravitational force on this object is G, mass of the Earth, times the mass of the object times the radius of the Earth squared. Okay. Now the radius of the Earth was known. This mass that's falling down is known, and G was measured. So you see, once the gravitational constant was measured in 1800, this is known, this is known. In 1800, well, okay, so this is known, this was known a long time ago. And as soon as in 1800, when this was measured, suddenly now you know the mass of the Earth. Okay. So that's why this experiment is called weighing the Earth, because once you figure that out, you can calculate the mass of the Earth. Okay. And so in 1798 is when we first knew what the mass of the Earth was. Okay. Now here's an interesting fact. So since we knew the radius of the Earth and the mass of the Earth in 1798, the density of Earth is mass of Earth divided by the volume of Earth cubed. And you can calculate the density, and it works out to 5.5 grams per centimeter cube. So the average density of the Earth. And if you go outside and pick a handful of dirt, what you find is the density of the dirt is about 2.5 grams per centimeter cube. Okay, so right instantly you know that there's the structure of the Earth has to be a little complex. There's got to be denser materials underneath. Okay. And so eventually we did figure all that out. And so here's the density profile. So here's the distance from the center. So that's the surface of the Earth. The radius of the Earth is 6,400 kilometers. Okay, about 4,000 miles. All right, so this is the density profile. So that's on the surface of the Earth. Like I said, the density is about 2.5 grams per centimeter cube. These are in kilogram per meter cube or gram per centimeter cube are the same. Okay. So about 2.5 gram per centimeter cube. And once you get in the mantle, at the bottom of the mantle, it's about 5 gram per centimeter cube. The outer core has a density of roughly 11 gram per centimeter cube, and the inner core about 14 grams per centimeter cube. So this is the density profile. Okay, as you go deep into the Earth. Now this shows you, I won't go dwell on this much because we got a lot of ground to cover. The internal structure of the Earth. Now we know the internal structure of the Earth in fairly nice, good detail, and this was surmised or interpreted. We deduce the internal structure of the Earth from earthquake data. When earthquakes, so if an earthquake happened here, earthquake wave travel all over the world, and all these seismometers placed all around the Earth detect these, and you can reconstruct the path of the waves that the waves have taken. Okay. P and S waves are primary and secondary waves. These are longitudinal waves, and these are transverse waves. S waves do not travel through liquids. S waves do not travel through liquids, so that's how come we know that the outer core is liquid. And anyway, so here's an earthquake that happened. This is a seismometer. This seismometer detected these earthquake waves, and we can reconstruct these paths back. And from the paths, from how the path curve, we can calculate the property of the material. So that's how we know the structure of the Earth. All right. So what this slide is telling you is, if mass is distributed uniformly, so the gravitational force exerted by a finite size spherically symmetric mass distribution on a particle outside the distribution. Okay, so the force that the Earth exerts on this satellite, it would be the same if the Earth were a point object in the center. Okay, so as long as the satellite is outside, and since the Earth's mass is distributed symmetrically, the force exerted by the Earth on this guy would be the same, even if you turn the Earth into a point object. Or for instance, if you turn the Earth into a black hole, the satellite motion would not change. All right, so here's the superposition principle. So for instance, this could be this could be the sun, and a couple of the planets and whatever. Anyway, here are three objects. The force exerted by this on this object and the force exerted by this guy on this object are independent of each other, and the net force on this guy is just the sum of all these forces. So this is the sum of that force and that force. And that's the superposition principle. So you can have many objects. You can calculate the forces of independent pairs, and the net force on any particular object is the sum of all the other forces. And that's what this formula tells you. Okay, so you've all measured G in lab, and G is, you roughly measured it to be 9.8 meters per second square. Okay, but that is the value on the surface of the Earth. That's the value near the surface of the Earth. If you go high enough up, and when I say high enough up, this height has to be comparable to the radius of the Earth. The radius of the Earth, remember, was 4,000 miles. So let's say if you find yourself 4,000 miles up above the surface of the Earth, now G will start being different. And so what this formula shows you how G will be different. Okay, so mg is gmm by r square. R is this distance. Okay, r is that distance, and r can be written as the radius of the Earth plus the height above the Earth. So this is the radius of the Earth, and this is h. because R square is RE plus RH square, and you can pull out RE square. And this, so what you get is GME over RE square, and this is what is the gravitation, acceleration due to gravity on the surface of the Earth, and that is 9.8. So G naught is that. And as you go higher and higher up, this term becomes greater than 1, and this term becomes less than 1. Okay, so if, for instance, you were 4,000 miles above the surface of the Earth, this would be 4,000, and that would be 4,000. So that would be 1. That would become 2. 2 squared is 4. This would be 1/4 of G naught. So 4,000 miles above the surface of the Earth, G will be about 2.5 meters per second squared. G at 4,000 miles, H equal to 4,000 miles will be 2.5 meters per second squared. Okay, so, and 4,000 miles, like I said, is roughly 6,000 kilometers, so it's G is that. Anyway, this gives you G as a function of altitude. Okay, and of course at infinity G is 0. Okay, what this graph says is, so if this were the gravitating body, or for instance it could be Earth, you are always attracted toward the center of the Earth, and the size of the arrow tells you the magnitude of the acceleration on you. So you see on the surface, these red arrows are the biggest. So on the surface, the magnitude, the length of these arrows would be 9.8 meters per second square, the magnitude of the acceleration. And this would give you the magnitude of the acceleration at that distance. Okay. So you see, the further away you go, the acceleration due to gravity gets smaller and smaller. And we saw that in the table before. These arrows are just showing you the direction of the acceleration. Okay, so you saw that as the altitude increased, the acceleration due to gravity decreased. And that's what this is showing you. Okay. Now here's a interesting idea. So let's let me do the following. Okay, let's say this is a bathroom scale, and you're standing on the bathroom scale. Okay, so what happens is, here's Earth pulling you down, mg, and you're not falling through the bathroom scale because the bathroom scale pushes you up, and that exerts a normal force. And this is the force that the scale exerts you on is your apparent weight. Okay, so for instance, do the following experiment. Here's an elevator, and you're standing in the elevator. So the elevator is, let's say, on the top floor of a building, and the elevator is at rest, so you're standing on the elevator. Now gravity is pulling you down, and this thing is pushing you up. Okay, and when the elevator is at rest, you will read your normal weight. Okay, now let's do the following experiment. Now we'll snap off the cable, and you free fall. And when you're free falling, what you'll find is the scale is reading 0. This will go to 0. Your apparent weight will be 0. Okay. Anyway, so what this slide is talking about is the following. Okay, so we understand what apparent weight is. So now, so let's look at this diagram. So this is looking at the Earth from the top. So here's somebody at here's something at the equator. So, and now the Earth is spinning. So this object is going around in a circle, and at the equator, the speed of this guy is about 1,000 miles an hour. Okay. All right. So, but if anything is going in a circle at speed v, we know that you need a centripetal force mv squared by r. Now, where's that centripetal force coming from? Okay, so there's only two forces acting on this object. Okay, the force of gravity in that direction. So the centripetal force, since it's in towards the center, gravity must be contributing to it. Okay, and then there's the normal force, which is your apparent weight. Since you need a centripetal force, this normal force has to be less than this force of gravity. If the Earth were not spinning, then this would be equal to the force of gravity. Okay. All right, so again, so the centripetal force has to be the force of gravity minus the normal force. And that's what's written here. The force of gravity minus the normal force is equal to the centripetal force. Okay. And and this is your apparent weight. So that's, we write that as m times g effective and g effect. So you can solve for all of this. mv squared by r, the centripetal force, can be written in terms of the angular velocity of the Earth. V is r omega. And so from there you can get this equation. Okay, so you can solve for the mass cancels. So, okay, let me go ahead and do this. So G minus G effective. Okay, I'm solving this equation. I'm canceling the mass, is R omega square. And so G effective, your apparent weight is G, apparent acceleration due to gravity is that. Okay. And this equation is interesting. So omega is the angular speed of the Earth. Okay. So if you made the Earth spin faster, this term would get faster, this term would get bigger. And if you spin the Earth fast enough, this term would equal that, and that's 9.8 meters per second squared. And your apparent weight could go to zero. Your effective acceleration could go to zero. So again, what this equation is telling you about is the apparent weight, your apparent weight. So this is, again, looking at the Earth from above. Let's say here's an object at the equator. And you can make the apparent weight of this guy to be zero if you spin the Earth fast enough. And you can do this calculation, put 9.181 meters per second square, put the radius of the Earth in meters, and you can calculate this. And what you'll find is if the Earth spun once in 90 minutes, okay, then this term will go to zero. You'd be weightless at the equator. Okay. Now you'll still have your normal weight at the North Pole. And as you walk from the North Pole to the equator, if the Earth were spinning once in 90 minutes, you'd go to zero. Okay. Your weight would go from normal to zero. Yeah, so that's what this graph is about. Okay. Of course, the Earth is spinning once in 24 hours, not in 90 minutes. So, so let's see what actually happens. Your weight is about 0.35% less at the equator than at the poles. So at the current speed, your weight at the equator only decreases by 0.35% of that. So this is only about 0.35%. This is only about 0.35% of 9.81 meters per second square. Okay. Anyway, and here's another interesting fact. So at the equator, like I said, if the Earth spun once in angular, if the period of the Earth Oops. So if the Earth spun once in 90 minutes at the equator, you would be weightless. And interestingly, that's the orbital okay. I thought there were some questions. Okay. Anyway, interestingly enough, 90 minutes, that's the time it takes for the space shuttle to go around the Earth. Okay, so those are related, those two facts. And in a space shuttle, you'd be weightless. Okay. All right. Now, here's another very interesting fact. Okay, so let's say, so here's the equator. Okay, and let's say you're building a building anywhere off the equator, so at a higher latitude. This would hold true both in the northern hemisphere and the southern hemisphere. So let me use the whiteboard. So what we're going to show you is the following. Okay, so here's the Earth, here's the equator. Now, here's the radius. Okay, so if you build a building here, now that will be perpendicular to the ground. Now it'll turn out that if you build a building anywhere at the north latitude, this is perpendicular to the ground. You'll have to build the building slightly tilted. Okay, and then again, if you go all the way to the North Pole, the building is vertical to the ground. If you're at in the southern hemisphere, the building is tilted like that. So only at the equator and at the poles are the building normal to the ground. Okay, and that's what we're going to show you. Okay, so hopefully you guys understood what I'm saying. Okay, so all buildings, so buildings in Daytona Beach and Palm Coast and all, they're not vertical to the ground. That would be vertical. They're tilted to the vertical. Okay, and here's what's happening. Okay, so if you're here, you're going in a circle. Okay, and so you need a centripetal force in this direction. Okay, and you can calculate your speed. Your speed would be the size of the circle you're going, and the Earth spins once in 24 hours. So the speed would be 2 pi r divided by 24 hours. Okay, r being this radius. And you can relate that to the radius of the Earth. But so, and that radius would be, r would be re cosine theta, where theta is your latitude. Okay. Now, where is that centripetal force coming from? So that centripetal force has to come from there's, so now let's think of a bob. This is a, what do you call these? A plumb bob. And here's the object of the bob. There's a force of gravity acting on it, and there's this tension in this string acting on it. Okay, so the force of gravity plus the tension in the plumb bob, those two forces must combine to give you the centripetal force. Okay, now the centripetal force is small, but nevertheless, and the tension is almost equal to that, but you can see that there's an angle. And so the bob is inclined at that angle, and that's the angle at which you build a building. Okay, so I hope you understood that. But again, so let's go back to the slides. So what we're saying is, on Earth, only at the equator are you building buildings. Only at the equators and the poles are you building buildings vertically. At these points, the buildings are built at an incline. Okay, and so off, and the buildings are tilted towards the pole. So for non-zero latitudes, Fs no longer points away from the center of the Earth. It is tilted towards the pole. A plumb bob will always point along this deviated direction. All buildings are built aligned along these deviated direction and not along the radius through the Earth. So for the tallest buildings, this represents a deviation of a few feet at the top. So what we are saying is, if for the Empire State Building, really it's tilted a few feet at the top. Okay, so I find it rather interesting. All right, I will pause the recording.